is HIPM equal to AI plus BI xi, not xi times AI plus BI. That's the question that is asked in probably extended manner, because we know that h can be written as sum over I into 1 to c xi HIPM of the mixture. So now this is of the form x1 times something plus x2 times something. So for a binary mixture it's equal to x1 h1 pm. So now the question is can we just take this to be h1 pm and this to be h2? Where we will have to work it out. You cannot just by inspection write it like that. That's the whole point. So my point is that now we can use either of the 2 or 3 methods that I have outlined for calculating the partial molar property. So I'm going to use this. In this case, binary it is h plus dh by dx1. Or rather, we know the formula 1 minus x1 dh by dx1, and so it will be h2 there are many ways of doing this. I think that the best way I have found to avoid errors is to write this in terms of x1 right at the outset, and not as a polynomial in x1 right at the outset. Then it becomes easier to do the subsequent manipulation, because if you just keep it as b2 times x2 or b1 times x2 times, and then even if you write it as 1 minus x1 and leave it like that and try to do the further operation, so basically I have to calculate this. So I always feel that the best way is to first express it in terms of a polynomial. All of these models seem to adopt. So what I am saying is merely for convenience. It depends on what you find convenient. Right? So at this point, over the years, I have noticed that it's easier to first 1 minus x1. So I have this. So now I will collect together all the terms involving x1, x1 squared, and the constant of at best. It's a polynomial of order 2 or 3 depending on the model. Right? So now I can easily see that this is a1 x1 plus b1 x1 squared. And then I have, let's do this first. I have plus a2. Right? 1. I'm going to take 1 and I'm going to take plus b2. And then I have minus b2 x1. Right? 1 times minus this. So I'll just put that here. So it's easier to just group them and just write these terms one below the other, so that you can collect together all the terms. So the moment I get an x1, I'll put this around with this, so that it can easily. Now let's do the other one. Again, I have minus a2 x1. I'm going to do this. Then I have minus x1 times b2. So minus another b2 x1. And then minus b2 x1 times minus x1 plus b2 x1 squared. Even though it's quite cumbersome to do it at the beginning, but if you try to now differentiate this with respect to x1 as it is, you are likely more likely to make errors. So if you are careful that you have done this correctly, that you have to check, and then it's easier from that point on. So now I can group together all these terms. If you want to write it as a polynomial, it's give me a2 plus b2, right, plus x1 times. I have a1 minus a2 minus 2b2. Plus b1 plus b2 x1 squared. The first thing that becomes easy, it now becomes, so we are just transferring the work before rather than after. So now it's very easy to differentiate. So this is h. dh by dx1 simply going to be a1 minus a2 minus 2b2 plus 2 times b1 plus b2 times x1. We are not done. We now have again h plus 1 minus x1 times this, right? So again, so h1 pm is again going to involve a fair amount of work. So instead of writing this, now I will simply write this. So I first write h, that's the first step. Now I have 1 minus x1 times dh by dx1. So first I do 1 times dh by dx1. So that will be a1 minus a2 minus 2. Again I am going to collect all the constant terms under one column. Again it's almost like a high schoolish type of instruction, but I mean I'm just pointing out a way of doing it without incurring too much error. If you have a better way of doing it, you are free to. Finally, what matters is whether you are able to get to the final answer correctly and not make mistakes in between. So we have 1 times dh by dx1. So I'm going to just put dh by dx1 here, right? The constant terms here plus 2 times b1 plus b2 x1. And then I have minus x1 times dh by dx1. So I have to do minus x1 of this. So this would be minus x1 times a1 minus a2 minus 2b2, right? Minus 2 times b1 plus b2 times x1 squared. So now I can gather together all the terms. So h1 pm is a2 plus b2, and then I have this is going to cancel. b2 minus 2b2 would give me a1 minus b2. So you can clearly see that it is not going to have the simple form, where in fact a quadratic. So it's not going to be just a1 plus b1 x1. And then let's collect together all the terms involving x1. So 2b2 will get cancelled here, right? And then I have a plus a1 and a minus a1, and I have a minus a2 and a plus a2. So a fair amount of terms are getting cancelled. So I remove that minus a2 x1 and then plus a2 x1. So that's also going to get cancelled. So I have 2b1 x1 plus 2b2 x1. So this will be 2 times b1 plus b2 times x1. And then I have minus b1 plus b2 times x1 squared. And so this is what we are getting. Let me see if this is what I have here. This is what we have. So clearly this is not equal to, this is not correct. So again, h2pm, you can do the same, because it's probably easier. I have everything there. H minus x1 is all I have to do. You can get that and check whether the gives you equal to satisfy. So this is one systematic way of doing it. To make it free of errors, and you will see that it will become even more complicated when you go to ternary mixtures. For instance, let's take this problem. U equal to x1 u1. So a ternary mixture plus x2 u2 plus x3 u3 plus c times, actually u1 u2 u3 are constant, so we are not going to, clearly you can see that u1 is the pure component property of pure component specific property of component 1. This is what we have. So first thing I want to do is get rid of x3. So now this is going to involve slightly more complicated calculation. So this will be x1 u1 plus x2 u2 plus 1 minus x1 minus x2 u3. So I don't want to have any x3 in it. So now we not only have to differentiate x3 with respect to x1 but also with respect to x2. So better to convert it to x1 and x2. So the two independent variables. Plus c x1 x2 times 1 minus x1 minus x2. So then I can gather together again x1 times u1 minus u3. There will be a whole group of terms, and I feel it is better to keep them separate because it will be easier to differentiate. So plus x2 times u2 minus u3, and of course I have u3 right at the top, right? And then I have plus c x1 x2. I can leave it as it is, but when you come to differentiating, it's easier to put them separately. Minus c x1 squared x2 minus c x1 x2 squared. It then becomes easier to. Now I need not 2 but 3 Gaussian molar properties. So what would be the formula for u1 pm? Let me write the general formula here, and then I have one of you come and write the. Let's write the general formula. So ui pm I equal to 1 to c minus 1 would be u plus du by dx I j equal to 1 to c minus 1 xj du by dxj. And then I have uc pm would be u minus sum over j equal to 1 to c minus 1 xj du by dxj. Right? So can someone come to the board and write what would be u1 pm in this case? This is now a ternary mixture. Ravi, when you come to the board and write, you just have to read off that from that formula. So write, yeah. So you write the sum fully so that you can see what by d is not first totally, now it's partial. You cannot even say it is dependent only on x1, right? Yeah. Minus, yes. Yeah, write that sum fully. Yeah, okay, first write it a equal to 1 to 2. I want it for c equal to 3. Yes. Yeah, that's correct. A equal to 1 to 2. xj again not, it should be partial. Only xj. Okay, now so you can clearly see you need to calculate not only du by dx1 but also calculate du by dx2, and the manipulations are going to be even more involved and tedious. But it's a straightforward procedure. It's all a question of how you organize your manipulation. That will determine whether you get the correct answer or not. This is not u1, it is du by dx1. No, you don't have to differentiate. Just leave it. Okay, this is fine. No, right, u3. This is u, okay, u2. Also right. u2. What is u2? That is the second. So the third one here will be different. The formula will be slightly different. One of the terms will be missing. dx2 minus same. That sum is the same. That is going to remain the same. So once you calculated the sum, you can use it for all three. You can calculate that maybe separately and keep it. Right? So u3 into something that's fine. So clearly, right? So all I need to do is calculate du by dx1 and du by dx2, and then we are done. The rest is just algebra. You have to do it carefully, and writing it like this will make it easier for you to do it. So first we have the constant terms. I'm going to figure x1, x2, and then we have the non-linear terms which are written explicitly so that it's easy to differentiate. Finally, you can group them together and then put them together. So it's quite easy. Now the Gibbs-Duhem equations, how many Gibbs-Duhem equations will there be? How many Gibbs-Duhem equations there will be? If you want to check, for instance, whether your calculations are correct, two equations, right? And they follow from the general sum over j equal to 1 to c. That's very important. Set j, or you can make it xj, du by duj dm by dxi. Let's say I want you to check whether the Gibbs-Duhem equation is satisfied or not. Right? So, if you want to check your answer, some of these answers are not given, but you can easily verify whether your final answer is correct or not. At least the analytical part. So, this is I equal to 1 to c minus 1. So, clearly now this would be, if you are going to write it, it's quite complicated, because then you will find that I have to, now for each of the Gibbs-Duhem equation, I have to now differentiate the partial molar property itself with respect to x1 or x2. So that will involve additional manipulations. Right? So, but if you write the Gibbs-Duhem equation 1 would be x1 du 1 dm by dx1. We have three terms. So x2 du 2 dm by dx1. Important to understand, to remember, if you want to remember it, apply it correctly, you remember that when we obtain the Gibbs-Duhem equation in terms of the n's, first we differentiate it with respect to ni, and we get the I Gibbs-Duhem equation. So the first Gibbs-Duhem equation will always have x1. The same thing we did for the mole fraction, we differentiated with respect to z1, right? And then we get the first. Then Z2 will get the second, and so on. We're not done. I have three terms in each of the Gibbs-Duhem equations. And then I have Gibbs-Duhem equation 2. It's a lot of work. You can just try it out to see whether you're doing the calculations correctly or not. This is again, we'll have dx2 as the now, once you have got the partial molar properties, each one of them you have to differentiate with respect to x1 as well as x2, and then again multiply by x1, x2. Again, when you multiply by x3, you have to write this as, it's convenient to write it as a sum here, but effectively to check, you would have to further convert it. So it's going to be a very long-winded calculation. You can see that even for binary it's quite tedious, but ternary will be even more tedious. Right? So I'll let you do some of these manipulations. Just do one or two problems, maybe one analytical and one. You can complete this, get Q1 DM at least. Right? Another way of checking is also, if you remember, we saw that mu I star, right? I equal to 1 to c minus 1. Mu I star is nothing but, you can write this as dg by dzi to put it in dp format. Right? Is equal to mu I minus mu c. Another way of checking. Right? There are many ways of checking. One is you can check whether this is satisfied. Once you have got the u, let's say, once you have got the 3, this is all the same. This is just a differential form of this homogeneity expression. You can check this, whether this is satisfied. There are many ways of checking your answers, right? And so another way of checking, let's say I have I equal to c 1 to c minus mu I star. So here it will translate into, for instance, du by dxi, right, is equal to these are the, we now take the whole of the partial molar properties, right? So this is nothing but dE by dzi. Now this answer UCC. So in this case, if you once you've got the three for the formulas for the three partial molar properties, one thing you can check in this, instead of checking the Gibbs-Duhem, you do much more involved. One way to check your calculation is to calculate U1 PM minus U3 PM and check whether it is du by dx1, which you have to calculate first. Right? Another one would be U2 PM minus U3 PM, whether that is equal to du by dx2. These two you have already calculated. Now, all these are equivalent representations of the homogeneity condition. So, there are many ways of checking your answers. It's important you keep all these things in mind, which one to apply where and which one to check where. It's entirely your choice. So, you have a lot of choice in the way you check these expressions. Are there any questions? So I urge you to solve the assignment problems and verify at least the answers that are given. For others, you know how to verify your answers. It's not that difficult. Most of them are binary, so it should not take you too much time to do at least a few of those problems. Now we'll move on to the next topic. We move away from homogeneous now to taking account systems mixtures in more than one phase. And to recall the corresponding development for a single component, we saw that we had the criterion for equilibrium. The criterion for equilibrium, which demanded that the temperature, pressure and chemical potential be uniform in a system at equilibrium. The criterion for equilibrium was the minimum energy criterion or the maximum entropy criterion. So if you recall that for that we considered an isolated system as replicated by Gibbs, for which all possible variations in the state of the isolated system, when we want to take the minimum energy criterion, all possible variations in the state which keep the total entropy, total volume and total mole numbers fixed, the energy of the equilibrium system is the one that is the minimum, right? So for that we gave a crude derivation of that by considering just two systems. We said that if the total entropy, total volume and total mole numbers are fixed for the equilibrium state as well as any other comparison state which is not an equilibrium state, because that's what we have to do. It's a comparison. Any maximization or optimization problem is a comparison. If you want to optimize a particular quantity, so we compare for what this particular state we desire, the equilibrium state, we compare the internal energy with all other states. For all the states, it's a constrained optimization because the total entropy, total volume, and total mole numbers are fixed. And we said that what distinguishes one state from another is how the entropy, total volume, and total mole numbers are distributed between the various homogeneous parts of a system. So to simplify that, we consider only two parts, and we said that this one would be. Now I'm recapping the derivation for a single component case. And so the total entropy is fixed. So that means the constraints are that S prime plus S double prime equal to S naught. And so also for a, so I'm going to consider any other state and the equilibrium state. For them, these are the constraints. B prime plus B double prime is equal to B naught. And then B n prime and then we wrote an expression for the energy of the system expanded about the equal. So we realized that the energy is actually can be written as a sum of the two parts. Right? So E prime will be evaluate any state corresponding to a particular distribution S prime, S double prime. This E prime plus E double prime. E prime depends on S prime, P prime, N E double prime depends on S double prime, P double prime, N double prime. But however, because of the constraints, the two S prime is not independent of S double prime, or rather S double prime is not independent of S prime, and so on. So I can write this as E of S prime, P prime, N prime. Just three of the variables, with the constraints appearing as parameters. So now we expand it about the equilibrium state. I get E equals dE by ds prime times S prime minus S equilibrium plus dE by dV prime times D prime minus D equilibrium plus dE by dN prime times N prime minus N equilibrium prime plus higher order terms. But then I look at this. This is dE by ds prime can be written as dE prime by ds prime plus dE prime by ds double prime, which in turn can be written as dE prime by ds prime plus dE prime by ds d double prime by, mixing up the primes and double primes. E is E prime plus E double prime. dE by ds prime is dE prime by ds prime plus dE double prime by ds prime. And then dE prime by ds prime plus dE prime by ds double prime times ds double prime by ds prime, which we can clearly see from here is minus 1. Right? So it's minus 1. And I recognize this as a term from the fundamental equation in terms of the extensive properties. dE is TdS minus PdV plus mu dN. So this I recognize in the temperature of the primed part. So I get this as T prime minus T double prime. Similarly, dE by dV prime will actually turn out to be P double prime minus P prime because dE by dV is minus P. And this could turn out to be mu prime minus mu double prime. And so we then said that the first variation, right, should vanish for E to be a minimum, right, or a maximum, first variation. And then I get the criterion that P prime equal to E double prime, P prime equal to E double prime, and mu prime. Now the only change here for mixture is all I have to do is, instead of N prime, N double prime, I have now N and I. Everywhere, the mole numbers are not just of one species but of C species. That's the only change. So I equal to 1 to C. So this now will be a sum J equal to 1 to C in J prime. And so the criterion would be to be retain the equality of temperature and pressure. Now since there are C chemical potentials, very easy to show that each of the C chemical potentials must have the same value in a system in equilibrium. Again, as we pointed out for the pure component system, for a homogeneous state, these criterions are superfluous. We don't need it because by definition, a homogeneous state is one where all properties are the same throughout the system. But however, the criterion for equilibrium takes importance in a heterogeneous. For example, you have two phases in equilibrium, right? Two phases in equilibrium. Not all properties are the same, but however, the criterion for equilibrium says that the temperature must be the same for the two phases. The pressure must be the same. The chemical potential for the pure component must be the same. Now for the mixture, each of the C chemical potential must be the same in the two phases. These are constraints that we have to take into account. As we saw how it is limited the number of degrees of freedom that we have if we have more than one phase in coexistence for the pure component. So same thing we have to take into account for the mixture. So clearly, now for the pure component, that means for instance if I have the criterion T1 equal to T2, two phases let's say, T1 equal to T2, and then mu1 equal to mu2. So applying this to the liquid vapor coexistence, for instance, right? We use the departure function. Now the departure function was already available because we had already calculated the departure function for G, and for the pure component G is equal to mu. Now so far in all of our calculations for the departure functions for the mixture, we have only calculated the specific property. We saw how to get E minus EITM and so on. These, we said, can be easily obtained. These are the specific for deviation or the departure function for the specific properties. Right? These can be obtained, we said, without proof, directly from the corresponding departure function for the pure component with suitable modifications. Right? One, the ideal gas state must be replaced with ideal gas mixture. The equation state will now become dependent on the composition, and we have mixing rules to incorporate that. Right? But however, now if I want to apply this, let's say between two phases, so this would take the form mu I1 equal to mu I2. So we need to be able to relate the chemical potential of each phase to some equation of state or some other quantity, whatever other quantities that are required, just as we did for the pure compound. We took the criterion for mu L equal to mu B. So we went to the departure function, calculated mu B minus mu IG. Then we went to the same departure function, calculated mu L minus mu IG at the same temperature and pressure. And we then equated the two. Right? And so, here again, so we need expressions for the chemical potential in terms of an equation of state. Right? So for that, what we need really is mu I, the departure from what we can get expression, we can relate to the equation of state is this is what we want. So far we have looked at departure functions for the specific property. Now this is like a partial molar property. We avoid it. Actually, for instance, this can also be written as sum over I equal to 1 to C, right? Zi times EIPM minus EIPM IGM. So we need it there also. Formula that would be very long, or you can try doing that. Getting the departure functions for the internal energy, enthalpy and so on is not as straightforward as it might think for the partial molar properties. However, one way is to calculate each one of the partial molar properties, the departure, the ideal gas mixture, and sum it up. Then you should get this. But however, we avoided this. This is quite convoluted. By a trick, you can prove that they can be directly obtained from the pure component specific property. Now you will see for the, this is like the partial molar property. Actually, it's nothing but GIPM. Now we are forced to deal with this because we incorporate or apply the criterion for equilibrium. I need a formula for the chemical potential, right? Which means I need a formula for the partial molar Gibbs free energy. So the problem that I avoided there can no longer be avoided. So I have to directly take that into account. So related here is what is called as the fugacity of a component in a mixture, which is defined. If you recall, the pure component, the fugacity was defined as P times Z exponential, so P times exponential. The departure evaluating the same temperature and pressure. This is the definition of the fugacity. Now we can define for the C component mixture fugacity by each of the component in the mixture, and that definition now I am going to give a 5 mix I equal to 1 to C is P times Zi, the P is the pressure of the mixture, Zi is the mole fraction. So I am not distinguishing between a liquid or a gas or whatever phase it might be, or even a solid. The mole fraction of, I am talking about a homogeneous phase, right? It has a certain pressure and a certain composition. That is the mole fraction of the component I exponential mu I of the mixture minus mu I of the ideal gas mixture, very important, both evaluated at the same temperature and pressure and mole fraction. Just as we saw for the pure component, you can also have departure function at the same temperature and volume, and they are quite different for the chemical potential as well as the entropy and a couple of other quantities. Right? So it is very important that the fugacity is always calculated for the specific heat temperature, pressure and chemical potential divided by RT. So this theory means that for the ideal gas mixture, the mixture itself is the ideal gas mixture. This would mean that the fugacity of any component ideal gas mixture is simply the partial pressure of the component in the mixture. Just as we saw that for the ideal gas, the fugacity equals its pressure. Right? And for the ideal gas mixture, the fugacity of each component equals the partial pressure of that component in the mixture. So, are there any questions? If not now, we will take up getting the departure function, which will directly give me the fugacity also, temperature pressure. Now we saw that when you look at departure functions for the pure component, you can, for E and H, the TP departure functions are equal to the TB departure functions. But for all the three other quantities that we considered, S, A and G, the two are not equal. Now if I want TP, I can work in the P domain. If we saw anyway, we have to move to the P domain because we want everything under the pressure explicit equation of state. Right? So one way is to calculate the departure function directly in the TB and then add the remaining difference. Right? For instance, I could look at this. The pure component, this will be integral 0 to P, as we saw, dU by dP minus right, and a particular temperature, so I will put this as P minus P here, dP. This is the direct formula. Now you will see that dU by dP is P. Right? So it's not in terms of P as a version of PND, but rather P as a version of PND. So the way to do it is to convert this to and so on, and then do a whole lot of manipulations, right? And then get to the final answer, which we did for S actually, if you recall. Another way is that this I can write first. So that can be very easily calculated. That this will be C infinity to T. But I know that I want this, right? One way to approach it is this is what I want to implement the criterion for equilibrium. Because the temperature and pressure of the two components are the same, so I can equate them directly. So now, if I want this, one way is to do it this way. Express it in terms of an integral over P, convert it to an integral over P, and do the integration by parts and so on, and finally get to the answer. Another way is, we know that dU by dP is actually P dP by dP. If I do this, I'll get the answer very quickly, as you can easily verify. But then I will have to, if I want this from this, then I will have to add, right? Because I know mu of dP is equal to mu of dP. So I will have to add the difference or calculate the difference. And we saw how to do that, because then we need only to the ideal gas. Now this is the approach I am going to adopt, because this will turn out to be easier than directly working in the P domain. So now how would the departure function for the chemical potential look like in the TP domain? The TP domain will look like this. You can easily show that it will have a very similar formula to the pure component. Integral 0 to t. I'm not going to go through that whole part again. So you will take this as given. Formula is very similar because the idea, as we said, it's effectively given out to be an integration only over t. T and z are fixed. But I am not going to do this. I am not going to adopt this. Rather, I am going to calculate this. But now I am going to make a further change. We saw how complicated the formulas are for the chemical potential of any partial molar property in terms of TB and Z or TP and Z as compared to TB and N. Right? Partial molar property, for example, are directly given in terms of the derivative with respect to Ni. But if we want to express the same in terms of, the mole fractions and the derivative of the specific function, how complicated it is. We saw that, right? So the same problem will apply. So now I'm going to make a somewhat different approach. I'm now going to express the chemical potential in terms of the temperature, the total volume, the total mole numbers. So this can be easily shown to be infinity to V by dV expressed as a function of d prime dn minus whole thing integrated over V prime, which varies from infinity to the actual volume V of the mixture. Now it will turn out that the two are not equal, right? But I will add whatever is required to get to this. So first let me focus on this. This is an independent problem in itself. Forget about this for the moment, how we are going to get to this from this. This is a problem of the departure function for the chemical potential in the volume, temperature volume space. Right? That I can pose as a different problem. It is not going to be equal to the fugacity. Right? It is not going to directly give me the fugacity, but I can look at it separately. Now, if I want to work Tp and N, basically I want a formula for this. So, which a fundamental equation you will look at? The chemical potential we saw can be expressed in terms of the derivative with respect to Ni, mu I, or in terms of E, in terms of A, in terms of H, in terms of G. 4 at least we have seen. Which one you would choose now? G. I am saying forget about this. Focus on this. What you are saying is true for the top part. Focus on V. If I want to focus on TVN, which function? Okay, one is wrong. D is not correct, so you are left with 3 more. Yes? That's okay. In terms of A, because A is directly given in terms of T, because why I want is I want this in terms of quantities related to their equation of state. Now if you look at this, dA, we've used this idea before for the properties of the ideal gas mixture. This is minus SdP minus PdV plus sum over J equal to 1 to C mu J dmj. Right? This is of the actual mixture, so we are not considering any particular mixture. Right? We have run out of time. But what I want to point out is that here is dA is of the mixture. dA by d, let's take the ith one, Ni, dB B nj not equal to I. This is what I have. But what I want here is not this, but the derivative of that with respect to B. Now if you see, this is dA by dNi, right? And this is B. This is dA by dB, right? So what I want is d by dB of that. Now I can interchange the order of derivative and write it as d by dNi of dA by dB, and that's going to give me minus dP by dNi at dB. So I have got what I wanted directly in terms of the pressure derivative with respect to the mole numbers. Right? You've seen how the pressure can be expressed in terms of the mole fraction. If I can express something in terms of the mole fraction, I can clearly express it in terms of the mole numbers. So we'll see how this will be directly related to an equation of state quantity in the next class tomorrow.